How's it going, ladies and gentlemen? Mr. Dunn here again, taking a look at 20.3 stuff, Voltaic cells. So our objectives are to describe the structure of a voltaic cell and explain what is occurring at an atomic level, as well as why it's occurring. So we talked about in the last topic about redox reactions and balancing them, but we never really talked about why do redox reactions even occur. And I'm going to tell you how I picture it in my head. So get ready for the roller coaster ride that is my brain. I like to think of each element as a different character. So these elements have personalities, right? And each element wants to be oxidized to different extents. Some of them love to be oxidized, like lithium loves being oxidized. Silver, not nearly as much. And you can find their activities on a chart titled activity series, right? So I'll have this over to the right showing you right now. This, is the activity series. So at the top you have the more active stuff. So the stuff that's more likely to be oxidized, and the stuff at the bottom that's less likely to be oxidized. So higher up on the series, the more active it is, the more it wants to be oxidized. If two elements interact and one of them is oxidized, there may be a reaction. Now here comes my brain pictures. All right, so scenario one, I got some sodium not oxidized, and I got some silver that's not oxidized. Sodium says, yo, you oxidized? Silver's like, nah, you? And you go, nope. He's all right then. No reaction. Nothing happens there. Okay? There's no conflict there. Scenario two, they're both oxidized. Sodium says, yo, bro, you oxidized? And Silver goes, yeah, I am. Me too, isn't it sick? Yeah, it sure is. What's with this guy? He's so weird. Still no reaction. Right? Alright, so this scenario. Sup, bruh? You oxidized? No, bro, I am not. Well, I am, and if one of us is going to be oxidized, it better be me. And that's great, man. There's no reason to take a threatening tone, right? Because if we take a look at this activity series that I've ignored this entire time, sodium is right here, and silver is down there. So we know that sodium wants to be oxidized more than silver. And right now, it is oxidized, and silver isn't, so there's no reaction. There's not going to be a conflict there, right? He's just making sure you know what's up. Got it. So weird, right? Seriously though, what's this guy's problem? No reaction. Scenario 4 is where it gets interesting. Okay, so we got sodium metal that's not oxidized, and we got silver ion, which is oxidized. And again, looking at the activity series, sodium wants to be oxidized more than silver. So something might go down here. Silver says, yo, bro, I thought I told you if any one of us is going to be oxidized, it's going to be me. Silver's like, yeah, well, what are you going to do about it? And then, bam, they start fighting and they have a reaction, right? And Silver's like, okay, fine. If you're going to be such a baby about it, you can be the one that's oxidized. And Sodium's like, all right, you're going to take that electron. Yeah. And so, yeah, that's right. You take that electron. I'm going to be oxidized, not you. Silver's like, whatever, man. I don't really care. I'm not that active. Not a big deal. So you get a reaction there. So that's my brain. Scary. All right, when will a reaction occur? Basically, when a more active metal is present with an oxidized metal that is less active. So, scenario here, how do you tell? Well, let's take a look. I got sodium. I look on my activity series. I go, hey, there's sodium, and silver is down there. And I see that sodium is the one that wants to be oxidized. And in this reaction, it isn't initially. So that's going to have to change. So I'm going to get a reaction there. All right, so an electron is being transferred from the sodium to the silver. So you get a reaction. What about this one? Will the reaction occur? Well, let's find copper, and I found copper over here, and let's find zinc, which I found zinc right here. So zinc is the one that wants to be oxidized more than copper. And if I'm looking at this, it's got a Zn of 0, or a charge of 0. Copper's got a +2. So we're going to get a reaction here because the thing that wants to be oxidized more isn't. So that's going to have to change. So we're going to get a reaction. Whereas, what about this one? All right, so I got Cu and Mg +2. Will this occur? Well, let's see. I got Cu0, not oxidized, and Mg +2 is oxidized. And it's the one that wants to be oxidized more. It's higher up. It's more active. And it's already oxidized. So you're not going to get anything that happens. It's going to be that scenario where it's like, yeah, I'm oxidized, and that's right. And that's nothing's going to happen. All right, so no reaction for this one. Cool. So redox reactions transfer electrons. Remember, we got reduction, which is gaining electrons, and oxidation, which is losing electrons. So what happens is, like, let's say I have a piece of zinc and I put it in some copper solution. What's going to happen is those copper ions are going to be attracted to the zinc, right? Because zinc's going, hey, what are you doing here, copper? Why are you oxidized? I told you before, I'm the one that's going to be oxidized. And then copper's like, okay, like, I guess we'll react then. And zinc's like, yeah, that's right, you're going to take my electrons. And then zinc transfers its electrons to the copper ion, which is going to, that's a redox reaction. We have zinc giving up electrons, it's being oxidized, and copper's accepting them or gaining them, being reduced, change in charges. Well, now what happens, though, is the zinc ion is going to be soluble. It's going to dissolve away. And what's going to happen over time is, as this keeps going, we're going to keep using up the copper ions. So the concentration of the copper ions is going to decrease. So copper ions give like a blue color. So that solution is going to fade over time. Well, what's also going to happen over here is, well, copper is no longer an ion. It's going to take on its solid state because it was reduced. And what that means is, over time, the copper is going to form a coat around the zinc that's in that solution. And you're going to get like copper plating onto the zinc. It's pretty neat. All right, did you know that electricity is moving charges? Whatever it is, electricity is moving charges, could be any form. And did you know that electrons are charged? I bet you did. All right, so if we could somehow trick the electrons go through a wire instead of directly to the other substance, we could use its power to power mobile devices, right? So like what I'm saying is, instead of having the electrons right here go, all right, well, I'll just go from there to there. If we could somehow separate them, and make those electrons go through a wire, we could use it to do work and stuff. All right, enter voltaic cells, also known as galvanic cells. I probably butchered that. I don't know. I'm in a mood, all right? So the first thing we got to do is we got to keep the two substances separate. So I got my copper ions and I got my zinc electrode. I'm going to keep them separate. I'm not going to put the zinc directly in it, because if I put the zinc directly in it, the electrons would transfer right there, and that's not what I want to do. All right, so now we got to connect them with a wire and our load, which is going to be powered in between. So our load could be our mobile phones, it could be another reaction, it's whatever we need the power for. So the load is just whatever is using up the power, right? And then you need an electrode at the other end. Generally speaking, you'll use the same element as what's in solution, because as it plates on, it'll just be copper, and then if you were to reverse reaction, then you would only give off copper. You just use the same element, all right? So you also need a solution containing the other ion. So you need a solution that has zinc ion in it. And you put it in like that. And now we're almost done. Almost there. We're missing something really important, though. It's called the salt bridge. So salt bridge is needed to prevent the buildup of charge in each of the half cells. So this is one half cell, and then this would be the other half cell. Together they make one voltaic cell. All the electrons moving to the copper side would create a negative charge on that end, which would repel more electrons from going to that side. The buildup of cations, which is a positive charge on the zinc side, would also make electrons less likely to leave that side. So let's take a look at what I'm talking about. We're sending electrons over, zinc's losing them to the copper ions in solution over here, but we got a buildup of negative charge because we sent electrons over there. We're also oxidizing the zinc to make more zinc plus 2 ion, which is going to make this side more positive. So if I was an electron, I know opposites attract. I'm going to be like, yo, I'm not going over there. I'm going to stay here where there's more positive charge. So to prevent that from happening, because if that happened, the electrons are going to stop going. We don't have any power anymore. We need what we call a salt bridge. Okay, so a salt bridge is usually a tube containing electrolytes, basically just some cations and anions that aren't going to react with our chemistry that we got going on. And it's usually in the form of a gel. So this allows for the flow of charge in the form of anions and cations between the half cells. So the reason I put that in bold is because it's not electrons. It's not electrons that are going across. It's the cations and the anions. All right, so what we got going on here is we got the electrons going from the zinc to the copper side, and they're going to reduce some of the cations, and the negative charge has to complete the circuit by going across the salt bridge. So the anions, the negatively charged ions, are going to go back to the zinc side, and the cations are going to go from the zinc side over to the copper side, so that everything stays neutral in terms of charge. But this is getting pretty annoying calling things copper side and zinc side because we're not always going to use copper and zinc and it gets just kind of obnoxious. So we're going to have names for these parts. The anode is going to be where electrons are lost. So we have oxidation occurring at the anode. So looking at what just happened here, which side's the anode? Say zinc. Zinc. Good answer. So the zinc side's the anode. It's where oxidation occurs and we call it the negative end. And the way that I think of it is because this is where we're shooting electrons out of. We got negative things coming out of there, so the anode, a voltaic cell, is negative. The cathode is going to be where the electrons are gained. So the other side, copper side, is the cathode. What happens there is reduction. So reduction occurs at the cathode, and it is the positive end. And I think of it this way. Electrons are being pulled to that side. So it must be positively charged. Cool. The load is what's being powered, so it's whatever you're using that power for. And the salt bridge prevents buildup of charge, prevents polarization. So those are the terms we're going to use from now on. Right, yeah, you've seen that, whatever. So, what's going on in voltaic cells? Well, first, electrons are lost at the anode, which will make cations, and travel through the load. So we got the electrons being lost, traveling through the wire and through the load, making cations. So we're making zinc plus 2 cations in this specific one, and those are going to dissolve into the solution. The electrons then enter the cathode, right? And they reduce the cations. So we have some of the cations being attracted to those electrons. It's going to reduce the cations, and the cations are going to be reduced. So the anions then have to flow through the salt bridge back to the anode. So we got anions, which are the negatively charged things, going across the salt bridge back to the anode, and we have cations flowing through the salt bridge towards the cathode. Okay. There's an awesome chemistry music video made by one Mark Rosengarten titled "You Start at the Anode," and it's fantastic. I suggest you guys watch it. I guarantee it will help you memorize everything that's going on. You start at the anode, electrons are lost there, and it keeps going. And it'll get burnt into your brain. All right, so a closer look at those electrodes, the anode. What's going on there? Electrons are being lost. So we have zinc losing those electrons, right? And cations are being formed. So as electrons are being lost, we're making these charged particles, these cations. Well, the cations are going to dissolve into the solution, which means what happened to the size of our electrode? What happened to the size of that? It got smaller. Okay? What's happening at the cathode? Well, electrons enter the cathode and they're going to reduce the cations, right? So we got this going on. And the cations are attracted to those electrons. And they're going, hey, what's going on, electrons? And they're going, nothing, I'm just hanging out. Well, that's cool. You want to reduce me? And they go, yeah, I do. So they reduce the cations. The cations get plated onto that electrode. So what happens to the size of that electrode? It gets bigger. So there's a way to remember these things. The red cat gets fat. So reduction occurs at the cathode, which gets fat, which literally gets fat. It gets bigger. And the red cat, right, reduction, cathode gets fat. So the red cat gets fat. The cations reduce and attach themselves to the electrode, and the electrode gets bigger. The anode will do the opposite. It's going to shrink. Okay, so to summarize, you need to be able to describe the construction of a voltaic cell, including labeling anode, cathode, load, salt bridge, etc., and describe the flow of particles in it, including the electrons, anions, and cations. You need to predict if a reaction will occur based on the activity series. Okay, so you need to one more thing: predict which will be the anode and the cathode. Right, so the way you're going to do that is the anode is whatever's going to be oxidized. So if I'm looking back at these examples, well, I'm going to go, all right, well, zinc is like up here and copper is down here. So I know zinc is going to be more active. It's going to oxidize. It's going to be the anode. So I also remember anox. Okay, and I think that's everything. Voltaic cells are pretty neat, batteries and stuff. Hope you found it helpful. I'll see you in class. Bring questions. Get back.